Hello, my name is Andrew, and this is my charge tape lab for Physics 2211. In this lab, I will analyze the interaction between tape pieces and other objects, and create a computational model to simulate the observed interaction. The purpose of this lab is to determine approximately how much excess charge is on one piece of the charged tape, using our knowledge on electrical force, electrical fields, and charges. The main result of this lab is that the tape had a positive charge of 1.307 times 10 to the negative 8 coulombs. The three important formulas that I use were Coulomb's law, the electric field formula, and gravitational force, where K in these formulas is a constant equal to 9 times 10 to the 9th. Also, one of the important concepts that I used was that like charges repel and opposite charges attract. The first part of this experiment was to quickly pull one piece of tape off of another piece of tape and then hang it on a table as shown here. From there, I put several objects up to it to see if it repelled or attracted. I observed that it attracted to my hand, which was neutral, repelled the other U-tape, which was positive, attracted to the table, which was also neutral, and attracted to a negatively charged pen. These observations led me to believe that the tape lost electrons when I pulled the U-tape up and off the base tape. And it also made me believe that the tape had a net positive charge, because like charges repel and opposite charges attract. The initial conditions of this lab is that the tape is neutral, the length of each piece of tape was 0.2 meters, the weight of the tape was 0.2 grams, which was calculated using the knowledge that the weight of 1 meter of tape is about 1 gram. The system was tape B, and the surroundings was tape A and the earth. Some of the assumptions I made was that the charge is equally distributed along the pieces of tape, and each piece of tape has an equal charge. The main experiment is shown here, in which I held tape A below tape B and observed the repelling force that acted onto tape B, pushing it up. The distance between these pieces of tape was 2.8 centimeters. This diagram here shows the electric force pushing it up, while gravitational force pushing tape B down. Even though there is charges acting all along each piece of tape, I decided to represent it as a point charge to make it more simple. Over here, I calculated the gravitational force acting on tape B, which gave a value of 1.96 times 10 to the negative 3 newtons. Since the tape is not moving, the gravitational force and the electric force are equal. So I set the electric force equal to 1.96 times 10 to the negative 3 newtons. Then I isolated Q, or the charge, and found that the charge of tape B was 1.307 times 10 to the negative 8 coulombs. In the computational models, I did the calculations very similarly to how I did the calculations for the observed. I set the constants here all above. Here is the gravitational force formula, F equals mg. This sets the electrical force equal to the gravitational force. And this line isolates Q and the electrical force formula. And on the left, it shows a free body diagram. The blue ball represents the tape A, which applies this force, this electrical force, onto tape B. And the purple arrow represents gravitational force acting downwards. The difference between the computational model and the observed was that the computational model was a little more precise. The computational model gave a charge shown here, and the observed shows the charge here. These two values are very close, and the difference is due to the small sources of error, which I'll talk about in the next slide. They're so similar because the computational model and my calculations use the same method to determine the charge. 1.307 times 10 to the negative 8th coulomb makes sense as a charge acting upwards on tape B, because we determined that both pieces of tape become positively charged after being pulled off the table quickly. Two positively charged objects repel, which causes tape A to go upwards. Possible sources of error in this lab are the same as the assumptions we made. We assumed that the charges are equally distributed along each piece of tape when really they are not perfectly equally distributed. We also assumed that each piece of tape had the exact same charge, where some charge on one of the pieces of tape may have been lost due to my hand. We also modeled the pieces of tape as a point charge when really the charge is distributed along the pieces of tape. So what if electrons had a positive charge and protons had negative charge? Well, the results would have actually remained the same. Like charges repel and opposite charges attract, so the tape would still repel. Why is it important to handle the charged tapes as little as possible? And what happens when charged tapes come in contact with your hands or other objects? My hand and other objects are generally neutral objects, so when my hand makes contact with the tape becomes more neutral because the excess electrons would transfer to my hand. So if I neutralized the tape with my hand and then tried to run the experiment, the two pieces of tape would be neutral and would not repel each other.